Hello and welcome. My name is Bob Tickleman. I'm a Microsoft technical trainer, and I'm here to inform you today in our series of what you want to know when you want to know it. This is part of the Designing Azure Infrastructure Solutions as part of the AZ 305 course curriculum. In this module, we're going to look specifically at data storage for our relational database, SQL for all intents and purposes, and the various forms of SQL that we have available to us. We're going to take a look at, what is the data storage that's available and where it fits into that category. So if you've taken that previously unstructured data type, this is just a very quick recap of that topic. But then we're going to start designing for SQL itself. And if you're familiar with SQL, you know that you have a thing called an MDF or master database file. Does it sit on its own drives, and how do you build those drives? And we're going to take a look at building a traditional SQL server. Maybe you're using IaaS or infrastructure as a service where you host that virtual machine. Well, then we have this whole set of offerings that fall into that platform as a service capability, where you can get everything from a thing called a SQL instance or a SQL database. And so you can have various forms of SQL that relieves you from having to manage this traditional infrastructure where you would have to build a Windows server, you would have to maintain that Windows server and patch it on a monthly basis. You would then have to install SQL on top of that SQL Windows server. You'd have to patch SQL on a regular basis, and you would have to build and manage the disk infrastructure for your log files, your transaction files, your temp DBs, and your MDF files that you're dealing with. Now, what you have as a platform, as an offering, as I said, you can get a traditional SQL instance and all of those characteristics that you would have from a SQL instance of managing backup schedules and working with security. Or do I want to go just to a SQL database? I don't want to have to manage all that other infrastructure. I just want to have just a SQL database available to me. And we'll take a look at some of the other features of things like elastic pools that are available for us. We'll then take a look at looking at security again. All information in a previous lesson we talked about everything is in Azure's encrypted at rest. We'll then take a look at other ways that you can encrypt that traffic so that in flight, as it moves from your secure database, secured and locally on the server, how is it now secured in transit to use of the application or maybe the end user destination? So we've got all these different features available to us. We'll then introduce a couple of other capabilities, looking at SQL Edge capabilities as a new form to be able to take a lightweight version of SQL and move it to the edge of your cloud infrastructure that you're dealing with, or that native or natural networking environment that you're dealing with. And then we're going to take a look at a feature called Cosmos DB. This is a relatively new feature. This falls into a lightly structured or non-relational database environment. SQL DB is a great capability to provide that traditional name-value pair, but it also provides capabilities for backwards compatibility to Mongo, Gremlin, Cassandra, all these other data types that you had, whether it be graph data, document data. And Cosmos provides 5 new levels of consistency that we never had before. So great capability to take a look at designing a new feature into your data solutions for non-SQL and SQL-based data. So let's get into the lesson. Across the 3 major categories of data that we have, unstructured data, semi-structured data, and structured data, we're going to be focusing in on those last 2 on the far center and the left of the screen. We've already covered unstructured data in another unit. But when we take a look at the categories, unstructured data is just this general, random file types, whether it's XLS, MP3s, movie files, JPEGs, .doc, .xls. It's that traditional mass amount of data that you're working with. As we get into semi-structured, we are looking at a lightly structured data type, also referred to as NoSQL. This is where you're going to get into things like Gremlin, MongoDB, got 2 tools called Azure Tables and Azure Queues, as well as Cosmos DB that provides this semi-structured data. We're also going to start off and take a look at a wide variety of structured data types. These are typically your relational database types, as well as SQL. And we have a full range of SQL offerings of highly structured data, sometimes also referred to as schema-based, because they follow a tight schema, which is basically a key or index of how the data is structured. It makes it highly optimized for storage of the data, retrieval, and manipulation from a business perspective. We're focusing in today on Azure architecture, and we're going to be taking a look at Azure SQL databases in all of its different flavors. So let's get into it. When you take a look at SQL as a highly structured data offering, these are special servers that typically get built. And these are servers that have, typically been deployed on premises, where you would build a Windows server, you would install SQL Server on top of that. And I want to clarify a term. People refer to that as a SQL server. Well, it is a SQL server that has SQL on it, but it has a thing called an instance. And by default, all of the resources of that SQL physical box or virtual, let's say it had 24 cores and it had a terabyte of RAM, all of them could be allocated to the instance of SQL on that server. That SQL server could have multiple databases on that server that would then share the resources added to that instance. If you wanted to dedicate specific resources to a specific database, what you would have to do is install 2 instances onto that physical server or virtual. So I could have a SQL server that had 2 instances of SQL on it. One that had multiple databases that maybe shared half of the resources. So maybe I gave half a terabyte and 12 of the 24 cores to one instance that would be shared across all of its databases. And I could have a second instance on the same SQL server that had 12 cores and 500 gigs of memory that were allocated to the one database that it was managing. So I really want to make a clear distinction between a SQL server, a SQL database, and a SQL instance. We have several options that are available from you, and I'm going to start from the far left-hand side. And there's one that isn't here. There's actually one called a SQL virtual machine in IaaS. So it's off the chart, we'll imagine, where you build a virtual machine, just like you would have on premises, and you have access to the base virtual machine, and you install versions of SQL on that. In my example I just gave you, from 1 or more. We're now moving into the focus of the screen, and we have a series of PaaS offerings where these are automated processes. And I'm going to walk through this for you in the demonstration, where you can have a platform as a service offering that builds a SQL virtual machine. So you press this button and it will automatically deploy a SQL server running a current version of Windows Server, probably 2019, 2022, depending on when you're watching this. And it's then going to deploy a current version of SQL on top of that. It will give you access to that virtual machine and the instance of SQL on there. So it's very similar to the IaaS version of the SQL deployment. And you would have access to having multiple databases, and you'd be able to connect using the SQL Management Studio to the instance and do all the maintenance cycles and all that kind of stuff that you would normally do with SQL. But you would have access to the base OS as well. Moving over to the 2 items that are in the middle, we have what are called managed instance, and these become true PaaS offerings. These 2 offerings that we have available to you will build a Windows server at the core, but you will not have access to be able to RDP to the server. As a SQL instance, as its name indicates, that second one from the left, it's going to give you an instance of SQL Server that you can deploy multiple databases in. But it's going to share the resources of the instance, just as if you had installed it onto a virtual machine in my example that I gave earlier. You would get all the management capabilities of an instance, like maintenance cycles and identities that are working within the instance. So all of those traditional capabilities of SQL instances, you would have access to it. You'd be able to connect to it with your SQL Management Studio to manage those characteristics. Moving over to the one in the dead center, you now get what's called an instance pool. This is going to be a slightly different version of a SQL instance. We're now going to get a grouping of devices that will allow you to have a pool of servers, be able to access, and then you can have it fully managed, and you're going to get features like automatic backup that are done automatically. Now, it doesn't preclude you from having to be able to do your own backup on your schedule, but know that there are some built-in features that are fully there for you. The patching of the OS, the patching of SQL is going to happen for those 2 internal ones. Moving to the far right-hand side, we're moving from instances of SQL over to single databases. Maybe I don't care about having multiple databases. I'm not a DBA. I'm not a database administrator. I'm a developer. I just need a database. And so we have options to deploy standalone databases that are built on SQL servers. And so you can see that second from the right. I can get a SQL database that has all those backwards compatibility to your on-premises, highly compatible, but I don't have to have all the management pieces that go around with it. I will not be able to connect to the RDP main host. I would not be able to connect to it with the management studio to manage the instance. I can only connect to the database and use it as a standalone database. And the far right-hand side, you get a thing called an elastic pool, which is going to give me a shared pool of databases that I can now split the resources, and they're called EDTUs, or Elastic Database Throughput Units, where I can now share a pool of resources. This is typically used in small, lightly used databases or in test and development environments that are very highly optimized for cost and performance, because I can now share the resources across a series of databases that are pooling those resources together. So maybe, the easiest example, let's say in a 3 8-hour days, I could have a pool that I'm using it for part of the day and you're using it for the other part. Or if we're lightly using it, as long as we're not at the same time peaking using it, which would cap it, we can now say I'm, using it for part of the day and you're using it for part of the day with only a bit of contention. It's a very effective way to be able to make that available. So those are a series of managed PaaS offerings from a standalone virtual machine, which provides a lot of those traditional characteristics, to full instances of SQL to individual databases. Today, we're going to be focusing on Azure architecture and specifically around some of the recommendations that we have for database scalability. So let's get into it. So when you take a look at scalability, SQL by itself has a number of capabilities that makes it highly available. Now, typically how you scale SQL is by adding additional SQL servers to those resources. Or you could potentially add resources to the single SQL server that you have. And you think about that, that fundamentally is going to make some big differences. Do I shut down the server? Do I add more services to it and add more memory and CPU and then spin it back up? Or do I add more instances to, say, a pool that cluster them together to share these resources? And that would be kind of a similar strategy to say, how do we scale this out and up? And depending on the type of offering that we're working with, taking a look at a previous module where we looked at the PaaS offerings, you're seeing on the slide the major groupings of SQL Elastic Pools, as well as the two managed instance, managed SQL instance and a managed SQL database, that will give you different options to be able to scale your solution and which ones, you're going to be able to scale up and out easier with, depending on where it goes. For all intents and purposes, when you add a SQL server, whether it be a database or a managed instance, adding resources to it is going to add it to all the databases that you're working with. And so you want to be a bit careful, because if you've got multiple databases on that server, all of them are going to benefit from that resource. Where if you want to be able to allocate it to a single one, maybe something like a standalone instance is going to be a better way to deal with this. And so they have some recommendations around the database scaling options for you, depending on the type of scaling you want and then the type of deployment that you're working with. The best way to get around this is properly scale your SQL servers before you deploy them, but we do give you options to scale out and to scale up the resources that are allocated to those PaaS offerings. Today, I'm going to be focusing on Azure architecture and specifically around solutions on SQL database availability. Let's get into it. We're going to start off first to take a look at some of the pricing models so you can understand where they fit into it. We've got 3 different versions of pricing that you can use. The DTUs are a way to obfuscate your need to be able to allocate specific resources to a specific server. The 3 major units of resources we take a look at are memory, reads, writes, and networking. So there's some kind of storage that goes along with this. And you would have to be able to know how my database is going to consume those resources. By having DTUs, they amalgamate all of those resources and you allocate DTUs, whether it's used for throughput or if it's used for reads, if it's used for storage, it doesn't really matter. A DTU is a DTU and can be spent anywhere across those different type of resources. And you buy DTUs in volume, and the more you buy, the cheaper they become. So it becomes a very easy way to be able to allocate resources without having to be able to be very distinct about the type of resource that I want to allocate it to. So if I over-provision, say, a SQL Server with more cores than it needed, but I under-provisioned it for disk throughput, I would pay that cost. I paid more for CPU, and I didn't pay enough for disk to be able to work in this. So this a way you can actually pay for what you use. Moving to the center, we get V cores. And so this way, you're paying a flat fee based on the number of cores that are being allocated, and how they're used doesn't really matter. Or if you're not using them, again, it doesn't really matter. But you might be over-provisioning and overpaying for those. So just another payment option. The serverless option is available to you, and you can actually deallocate and have time starts and stops of these resources potentially. Know that it's not available for all deployments of your SQL Server, but this becomes a very cost-effective way to say, if I know I've got periods of in or no activity, you can actually turn that consumption off and have a very cost-effective way to manage the allocation of resources. When you take a look at the high availability options, we take a look at the high availability of SQL in general, and you're going to see different tiers of SQL servers that we can deploy. This slide's going to cover the general and standard tiers. And what we do is do local copies of the data. This is very similar to some of the always-on replications that you're dealing with. And so you're seeing at the bottom, it uses LRS, RAGRS as ways to replicate that copy data in the local region that you're deploying this. And it guarantees that write operations are going to be committed to at least one other instance of the deployment that you're working with. And so this is very similar. It's not quite clustering, but it's like an always-on replication group that you're dealing with to make these highly available for you to work with. As the next service tier, we get into business critical and the premium tier. And this is going to actually have active nodes that are working, again, doing a lot of that log shipping and replication of the always-on replication components that are available for a SQL Server. Again, this is the PaaS offering that provides the configuration that you would have had to have done if you were building this yourself. And so if you thought about how you would deploy SQL Server, we've broken them up into kind of a standard tier, these premium tiers that provide higher availability and failover capacity, so that if you lose one of the nodes, you're not going to have reduced functionality because you have more than enough nodes to take on the workload for the failed node that you're dealing with. Moving to the last of the tiers, we move into SQL Hyperscale. Now, this is, for me, a really exciting feature when I saw it come up. What we've done is something that no one else on the planet can do. Other cloud services could possibly cluster SQL servers, but because we own SQL Server, we actually fundamentally tore apart and rewrote SQL as a cloud-native service. And I encourage you to take a look at all the documentation around this from an architect's perspective. If you're a SQL manager, you probably know some of these. But what it's done is it's fundamentally ripped apart the different components of SQL from memory and caching and compute and made it a cloud-native application. So as opposed to having to add physical servers or virtual servers to add more CPU or more compute, it's actually just available for you and makes a whole bunch of stuff nearly instantaneously accessible. So for example, adding storage, there is really no limit, where in the past you would allocate a specific amount of storage to your MDF or LDF, your data files locations you're dealing with. And if that disk ran out, you would have to re-provision that environment. This just continually expands and grows in a nearly instantaneous availability. You can add a number of servers and cores. I remember when I saw the first example, they took a SQL Hyperscale server that had, I think it was 100 cores, and they slid a bar up and they added 3,200 cores to the SQL Server. All of these features, again, mind-blowing, but it fundamentally changes the way that you look at SQL Server. Backups are more efficient. Recoveries are faster. Allocation of resources, limits are basically gone. So SQL Hyperscale is maybe a great way to take a look at, a new way to deploy your SQL servers. And you can scale it way back down. It's not just for big throughput numbers. and it doesn't have a big cost. It just depends on what you're using, and it provides some of that scalability for you. Today, we're looking at Azure architecture, and specifically, we're going to take a look at securing your data in all the formats that might exist within inside of SQL, at rest, in transit, as well as in use. So let's get into it. When you take a look at databases and the storage of data, you want to take a look at all the different states in which that data exists. When you take a look at a database, and so you actually have data protection, or a thing called an MDF. So there's a data file of an MDF file that has all of your tables inside of that file. That file exists on a hard drive. That hard drive is then going to be accessed through a network or an application accessing that information. So let's just take a look at all this different data and how it might be secured and what you can do with it. So let's go right into the data tables themselves. Inside of a database, I've got secure information, maybe a identity number, maybe it's a credit card number, and I need to be able to mask some of that information from general users. So for example, I need to know your credit card number. Maybe I've got it on file, but maybe you're calling into a help desk and they're going to use that information to identify you as a unique user. Maybe it's a social security or social insurance number. Having the entire number is a security risk. What we can do at the data level is to mask that data. And this is why they often say, can you give me the last 4 digits of your social insurance number if you're in the United States? Or in some other place, they can say, can you give me a couple of digits to your credit card? Because for unauthorized users, we're able to mask the data from unauthorized access. That's at the data level. We can encrypt entire tables. We can encrypt the MDF file itself. So as SQL, the operating system starts up, SQL starts up, and it needs to access the database file, the MDF file, the table and or the MDF file itself could be encrypted. And you're seeing these different levels of encryption listed for you. So now we've been able to decrypt the file. At the operating system level, we can encrypt the drive. And so now you have to be able to decrypt the physical drive. So if someone were to be able to take the server, they won't be able to get access to the drive because the drive is encrypted. Well, that's great. Now we're taking a look at data in transit and data in use are the other terms that this section was talking about. So I've been able to mask the data. I've been able to decrypt the table. I've been able to decrypt the database file. I've been able to decrypt the hard drive. That's great. But I now need to copy that data into the application for its use. So I've got in transit features that I need to encrypt that data or make sure that it's safe. And you're taking a look at some of the terms of VNets, firewall rules, NSGs, private link capabilities are all covered in other portions of this course. And we have TLS for data in flight, all of these different features for us to be able to make that data seamlessly available. And everything I've talked about so far is independent of the application. This is handled at the infrastructure level. But now my data exists someplace, usually in an application, and I could potentially, it's called end-to-end encryption. This takes in a little extra work to be able to configure, but I can actually have the data at its end use point be secured and encrypted so that if you have the end user or the end unit that is managing consuming that data, if it gets compromised, you're going to be able to protect the data. So there's a wide range of services that we have available for us to be able to secure and lock down the data. Now, one that I haven't talked about is that second from the left. There's a whole full set of identity and authentication and authorization using RBAC, using SQL authentication, providing identity and locking down the files and giving access. So we've got a full range of those kind of permissions that are available to us as well. When you take a look at SQL, a lot of these things I've said are separate from SQL. You take a look at the Microsoft Entra ID. They've got it listed as Azure AD on the slide. It's been replaced by Microsoft Entra ID or even your on-premises domain controllers. SQL Server itself has the ability to authenticate user accounts within the SQL Server. So often you're asked, are you using a SQL account that is unique to that SQL Server, or do we have an identity that we can accept from a known identity provider. And in other modules, we talked about the broad range of modern identities that are available to us through Entra ID, whether it's in a business to consumer model, or from an internal environment we're working with, or through a hybrid environment back to our Active Directory Domain Services environment. Today, we're focusing in on Azure architecture, and we're going to take a look at a feature called Azure SQL Edge. So let's get into it. In other units, we've covered a wide variety of options available from SQL. We've looked at the traditional SQL running on a virtual machine, through to a wide variety of managed components working with the platform as a service offerings. We then took a look at SQL Hyperscale as an option for us. In this modern world of IoT and remote disconnected devices, Microsoft has had a need to be able to come up with other options to have a highly functional relational database, providing backwards compatibility to the traditional SQLs that we're working with. SQL Database Edge is that tool that allows for autonomous operation of this fully schema-based, highly structured data environment to work either in an online or offline environment. I want you to think of maybe an autonomous car that may or may not be connected. There's a ton of telemetry information coming from a wide variety of sources on that vehicle. That information needs to be gathered and potentially uploaded to a database. Well, what happens if that database is not available to have it uploaded? I can't have the autonomous car not be available to us. And that's where SQL Database Edge, or SQL Edge, is going to provide this capability for us. It's a containerized application, as I said, can run online or offline, anywhere that you can run that container, and provides all those traditional features and functions that we loved about SQL Server itself. And they're now available in this environment. And whether it's used and computed and calculated locally, or if it's used to upload that data to a full SQL Hyperscale engine, maybe, we have this end-to-end solution that meets a wide variety of modern needs and requirements. Today, we're looking at Azure architecture, and we're going to focus in on Azure Cosmos DB and some of its use cases that you might want to use to architect into your solution. So let's get into it. When you take a look at the wide variety of data that's out there, and we've talked about the different classifications of unstructured data and the storage accounts that we have to optimize that, we've taken a look at the structured data using the different versions of SQL that provides that schema-based environment. We've touched a little bit on some of the lightly structured data, and it's been made available through Azure Tables, as well as things like Redis Cache. MongoDB and other database types all fall into this category of no SQL or no schema-based infrastructure. Now, a lot of them had limitations, and I'm really excited about this feature called Azure Cosmos DB. It not only brings at a hyperscale massive capacity for us, it also introduces 3 new levels of consistency that never existed before across those traditional data storage types, whether it be Mongo or Azure Tables. Azure Cosmos DB is a fully managed NoSQL deployment that is globally available in all regions within Azure. And it has backwards compatibility. You'll see this over the next couple of slides with a wide range of APIs. So if I've got a MongoDB with Mongo APIs in my application calling it, where I have to build multiple Mongo databases to manage my infrastructure, I literally could take my Mongo application, migrate my data in a standard format. I don't have to do any transforms on the data. I could take that Mongo database, upload it into Cosmos DB, and point my Mongo data application using its APIs at Cosmos DB, and literally switch and replace it. So there's some massive capacity and capabilities. I'm going to get the benefit of these 3 different new types of normalcy that we're working with, or consistency. Most databases work on what's called strong or eventual. That either puts the burden on the database to manage the consistency level of the data. You'll hear other terms called normalization. So if you have a primary read-write copy, it needs to normalize that data or make sure it's at all copies, versus strong puts that's eventual, where it puts it on the application that need to do it. Or if you go to a strong replication, it puts the burden on the database to do this. We now bring in these 3 new copies to get into bounded staleness, and other types that we can now group structures together and manage the order in which these updates are going to take place across the multiple copies. Another big advantage of Cosmos DB is some of the throughput, global scale, replication types I've mentioned. But one of the other things that we have is you take a look at, say, something like Azure Tables. As a non-relational data storage, it can tap out at about 20,000 operations per second. So it's, very capable, but it doesn't really have large scale, enterprise scale capabilities. You take a look at something like Redis Cache, doing a lot of the same data structures. You can get up to 160, 180, 200,000 IOPS at Redis Cache. Cosmos DB gets you into the tens of millions of transactions with sub 10 millisecond latency times at a global scale. So again, it's the same data structures providing backwards compatibility. It's kind of that one ring that rules them all for me, that does everything you want it to do at massive scale, keeping all the data formats and the structures that you're used to. So there's a bit of a sales point to, the look at Cosmos DB. When you take a look at the default API types, I mentioned this previously, that the Azure storage tables, which is one way to store data using a storage account that is going to be regionally based, we could take an application that starts off maybe as an Azure table. It's cost effective, but maybe your organization grows beyond a single region. Maybe it grows through a throughput requirement or the complexity of being able to have different consistency levels. I could literally migrate that data into Cosmos DB, keep the applications the same, call the table APIs, and now provide that massive capacity to that application as it grows. So it's a great way to kind of crawl, walk, run in your application development. Here's a slide that shows this wide variety, as I said, MongoDB, Gremlin. So whether I'm using with graph data, if I've got table data that I'm working with, we've got a solution using the appropriate API. Okay, so we've shown you a variety of non-relational and relational data types, sometimes referred to as semi-structured or non-SQL versus highly structured or SQL data. And they fell into those categories of the various flavors of SQL. And then we saw that we added Cosmos DB as well as this one that we just showed you on the slide, Azure Tables, which is part of a storage account. But we have a wide variety. I love the line of, if all you have is a hammer, everything looks like a nail. In the past, we only had one type of data from a relational basis, and that was SQL. And everybody put everything there. Now you get this variety of options that are available for you. So you just don't have a hammer. You can have a variety, and building a solution is really going to be not your job to actually program or design the actual data solution. But as an architect, I think it's important that you ask the right questions to make sure that the right data type is being selected. So let's get in and take a look at a number of them. Quite a few of them. I'll try and hit a couple of them and maybe you show some similarities, especially when we get into the SQL. So let's get into that demonstration. Looking at the SQL Server options that we have available, we talked about having SQL Server on an IaaS or infrastructure as a service. That's where you would have a traditional VM that you would deploy, you would then patch and maintain, and on top of that, you would install SQL instances that you would then be able to manage and work with. We're going to be focusing on the SQL PaaS offering. Starting from the right-hand side here, we have SQL virtual machines, but you'll see that we have a variety of machines that are like a virtual machine where you would deploy in an IaaS offering, but these are PaaS offerings, and we get a full range of SQL servers that we have available for us. Showing the details, you'll see that this is a virtual machine. It offers that full Windows administration capabilities, both at SQL and the underlying OS that you're working with. Taking a look at the next offering over, we can then have a SQL managed instance. This is going to be slightly different than what we had from the SQL Server, where we had access to the base operating system. This is going to give us access to a full SQL Server access, but you're not going to have access to the underlying operating system. And so you can have a single instance as well as one that is going to go with a feature called Azure Arc for administration. Moving all the way up to the full PaaS offering capabilities, where maybe you don't want to manage a virtual machine and SQL. You don't want to manage just SQL. You want to just manage a database. And so we have single database options that fall into a single database, an elastic pool, or a database server where you could actually have a single database. And looking at the features that we have available here, moving on to Cosmos DB, we talked about some of the great capabilities of Cosmos DB, being able to provide a wide variety of data types that you're dealing with. And you can see here, when creating a Cosmos DB, you can select, is it going to be a NoSQL, Postgres, MongoDB? You got your Apache Cassandra, you got your Azure tables. So we've got a wide variety that you can build, and we'll then go in and take a look at some of the replication model types that we have. There's quite a bit of configuration to do as a Cosmos DB administrator. But as an architect, the key features you want to know is that Cosmos is an Azure core service that is globally available. So what you can now do is build a Cosmos infrastructure, either initially or expand it out after its initial deployment, to be a global distribution across every region that we support in Azure. So you now have a globally distributed, high resiliency, fast throughput database that you're working with multiple consistency levels. So the global distribution capabilities are available for you. Taking a look at the consistency levels, we talked about the 5 levels. Strong and eventual have been around for many years within a database world, and we're going to take a look at those 2 first, and then we're going to take a look at the new features of bounded staleness, session, and consistent prefix. Now, a traditional SQL deployment is typically deployed as a strong replication. So you have an original writing copy or a read-write capability, or your primary database. These writes would happen at the primary location, and then it would need to replicate to all other replicas before that value gets recognized and is consistent in all locations. And so you're seeing that information, it writes consistently across all copies before that information is available. Moving all the way down to that eventual session, this has been available again for SQL for many years. And what this will do is you still have a single read-write copy, your primary copy you're working with, and then you have multiple other reads. But you'll notice that as this information on the primary writes that data, you're seeing an inconsistent replication of that information across all the multiple copies. And it will eventually normalize across all the copies you're dealing with. Now, this requires quite a bit of work from the application developer to be able to withstand a non-normalized database across read copies that you have out there. When you take a look at these 3 new versions that are available through Cosmos DB, we then get into these features, things like bounded staleness. And so in here, you're going to be able to bind copies. We still have one read-write copy with multiple read versions, and we're going to be able to bind a specific read version based on the number of version changes from the original, or the time interval between that lag of writing it to the primary and then the secondary copies. So we have 2 options to be able to do that bounded staleness. And so what we're seeing is between US West 2 writes and then reads, you can see a tight coupling of those values being put together. But then we saw that in East US 2 and in Australia, we have this potential delay. So they still get written across the multiple copies in the very specific order, but you might have a delay between one copy and other copies within that set of databases that are configured for your global distribution of Cosmos. We then take a look at the session consistency, and this is going to provide the copies that might be shared across a single session that they need to stay in a specific state of consistency. So here we're seeing that these 3 copies of US West, the writes read for a session, that session is going to require that everybody that might be part of that same session, they need to have that information consistent. And you're seeing across session B, that information still gets written in a specific order, but it's delayed from the original bounded sessions that you're dealing with. Then moving into consistent prefix is that final new copy we're dealing with. This is going to talk about the sequence of the writes across the multiple copies being in a very specific order, but again, they're going to appear in an unbounded state where it's going to happen unevenly across the multiple copies you're dealing with. Strongly encourage you to take a look at what those features are going to do. And as an architect, not your responsibility to pick which one, but as an architect, it's a great idea for you to ask the question of, would you benefit from, new consistency type, and then have that database developer pick the type that they're working with. Let's return back to the lesson. So welcome back from the demo. There's a lot of information in there. And again, as I did the intro to the demonstration, don't think that as an architect, it's your job to have to actually make some of these choices. Your job is to ask the questions along the way. And I gave you some of those questions as I did the demonstration. those are the questions that you want to ask of your data storage person to say, hey, do you need a SQL database? Does it have to be a managed instance? You don't know what that is, but they should be able to answer that question, because their tendency will to go to what they know. They may not be aware of all these different solutions. And so if they don't need to have a full managed instance, maybe a SQL database is better. Do they have to have it on a managed server that they need access to the physical server? Then you want to also start taking a look at some of these other data types. We took a look at Cosmos DB as a way to store that information at scale that, people used to rely on SQL to do, and they couldn't get it from in the past, Mongo or Cassandra. So we've got this wide variety. Remember those questions that I gave you along the way to build into your architectural solution. There's reasons to have relational database and SQL as systems of records. I would then step down and take a look at Cosmos as an option for you to be able to do that. And then you look at some of the other features of Azure Tables as ways to get some of that lightly structured or fully structured data. So thanks for participating in this lesson. I look forward to seeing you at a future one.